Look up into a clear, moonless night sky, far from the glare of city lights. You will see it, a tapestry of pinpricks scattered across a velvet abyss. Some are brilliant, defiant beacons. Others are so faint they flicker at the very edge of perception. For millennia, we believed this was the extent of creation. A celestial sphere, a dome of fixed stars, placed there for our benefit. A comforting, finite ceiling above our world. But what if that ceiling is an illusion? What if each point of light is not just a distant fire, but a sun like our own? And what if the dark spaces between them are not empty, but are filled with other suns, other galaxies, so far away their light is lost in the immensity? This is the story of a journey to measure the immeasurable. It is a quest that shatters our sense of scale, our place, and our own significance. We ask a simple question, a question a child might pose. How big is the universe? But the answer is anything but simple. It is a story of paradox, of cosmic horizons, and a reality so vast it strains the very limits of human imagination. To truly grasp the answer, we must first unlearn everything we think we know about space, about time, and about the very nature of seeing. Our journey begins not with telescopes, but with geometry. 2,500 years ago, the ancient Greeks performed one of the first great intellectual leaps in cosmic measurement. They understood a principle called parallax. Hold your finger out at arm's length and close one eye, then the other. Your finger appears to jump against the distant background. This apparent shift is parallax. The closer the object, the more dramatic the jump. Greek astronomers, like Aristarchus of Samos, reasoned that if the Earth orbits the Sun, then the nearby stars should also appear to shift against the backdrop of more distant ones throughout the year. They looked for this stellar parallax, and they found nothing. Not a flicker, not a wobble. Their conclusion was logical, but profoundly wrong. They believed the stars must be relatively close, fixed to a single crystalline sphere, and that the Earth must be stationary at the center of it all. The truth was far more staggering. The stars were so mind-bogglingly distant that their parallax shift was too minuscule for the naked eye to ever detect. The universe was already proving itself to be vastly larger than our senses, or even our cleverest theories, could initially comprehend. For nearly 2,000 years, this geocentric, finite model held sway. It was a comfortable, human-centric cosmos. Then, thinkers like Copernicus, Galileo, and Kepler began to dismantle it, piece by piece. They placed the sun at the center of our local system, and in doing so, they demoted the Earth. But even they had little idea of the true scale of what lay beyond Saturn. The stars were still largely considered a shimmering backdrop to our solar system's dance. The real breakthrough in measuring the stars had to wait for technology to catch up with theory. In 1838, the German astronomer Friedrich Bessel finally succeeded where the Greeks had failed. Using a powerful new telescope, he measured the parallax of the star 61 Cygni. The shift was impossibly small, less than 1/3 of an arcsecond, equivalent to the width of a human hair seen from 60 feet away, but it was there. And the distance it implied was staggering. Over 60 trillion miles, or about 11 light-years. For the first time, a human being had wrapped a measuring tape around a star. The first rung on what we now call the cosmic distance ladder had been placed. The floodgates of cosmic scale were beginning to creak open. But even this colossal distance was just the measurement to our next-door neighbor in a city of stars we had not yet even recognized as a city. By the early 20th century, astronomers knew we lived in a flattened disk of stars, a celestial river of light we called the Milky Way. The dominant view, championed by the influential astronomer Harlow Shapley, was that the Milky Way was the time's entire time's universe. The countless stars we could see, the vast clouds of gas and dust, this was it. Everything. There were, however, some mysterious smudges in the sky. Faint, spiral-shaped clouds called nebulae. Shapley and many others believed these were just nascent solar systems, forming within our own Milky Way. But a few, like Heber Curtis, argued for a more radical idea. They contended that these spiral nebulae were in fact island universes, entire galaxies, just like our own Milky Way, but lying at unimaginable distances. The debate came to a head in 1,920 inches, what became known as the Great Debate. It was a clash of titans, a battle over the very size and structure of reality. But without a reliable way to measure the distances to these faint smudges, the debate ended in a stalemate. The universe hung in the balance, its true nature hidden behind a veil of uncertainty. To pierce that veil, science needed a new tool, a new kind of ruler. That ruler was discovered not by a famous professor in a grand observatory, but by a quiet, meticulous woman working as a human computer at Harvard College Observatory. Her name was Henrietta Swan Leavitt. Her job, for which she was paid a meager 30 cents an hour, was to catalogue the brightness of stars from photographic plates. She was not even allowed to operate the telescopes herself. Yet, in her patient, painstaking work, Leavitt noticed something extraordinary in a class of stars called Cepheid variables. These stars have a peculiar quality. They rhythmically brighten and dim over a period of days or weeks. Leavitt discovered a stunningly precise relationship. The brighter a Cepheid was intrinsically, the longer its period of pulsation. Think of it like a lighthouse. Imagine you see a lighthouse in the distance, but you don't know how far away it is. If you somehow knew it was a massive 1000 watt bulb, you could calculate its distance based on how faint it appears to you. Leavitt had found the cosmic equivalent of the bulb's wattage. By measuring a Cepheid's pulsation period, astronomers could know its true intrinsic brightness. By comparing that to its apparent brightness in the sky, they could calculate its distance. Henrietta Leavitt had handed science a standard candle, a ruler capable of measuring distances not in trillions of miles, but in millions of light years. She had forged the next, crucial rung on the cosmic distance ladder. The key to unlocking the universe now lay in finding a Cepheid variable within one of those mysterious spiral nebulae. The task fell to a brilliant, ambitious, and notoriously difficult astronomer named Edwin Hubble. Perched atop Mount Wilson in California, he commanded the most powerful telescope on Earth, the 100-inch Hooker telescope. Night after grueling night, Hubble aimed this colossal eye at the largest and most famous of the spiral smudges, the Andromeda Nebula. He took long-exposure photographs, searching for the telltale flicker of a Cepheid. In October of 1923, he found one, and then another, and another. He carefully measured their pulsation periods. Then, using Leavitt's groundbreaking period luminosity law, he performed the calculation. The result was earth-shattering. The number he calculated was nearly 1 million light-years. It was a distance so immense, so far beyond the known boundaries of the Milky Way, that it could only mean one thing. Andromeda was not a cloud of gas within our galaxy. It was an island universe, a galaxy in its own right, a sprawling city of hundreds of billions of stars, separated from us by a gulf of intergalactic space so vast that the light he had just captured began its journey when our human ancestors were still learning to master fire. In that single moment, the known universe expanded 100-fold, 1,000-fold, 1,000,000-fold. The ceiling of the cosmos had not just been cracked, it had been obliterated. Our galaxy was not the universe. It was just one of countless others, adrift in an ocean of unimaginable scale. Humanity was, for the first time, truly lost in the cosmos. But Hubble's work was far from over. As he measured the distances to more and more of these newfound galaxies, he began to analyze their light. He passed their faint glow through a prism, spreading it into a rainbow-like spectrum, and in these spectra, he discovered something profoundly strange. The light from nearly every galaxy was stretched, its spectral lines shifted towards the red end of the spectrum. This phenomenon, known as redshift, was a cosmic Doppler effect. Just as the pitch of a receding ambulance siren drops, the wavelength of light from a receding object stretches, becoming redder. What Hubble found was not just that galaxies were moving away from us. He uncovered a distinct pattern. The farther away a galaxy was, the faster it was receding. This was a revelation that would forever change our understanding of reality. The universe was not a static, eternal stage upon which galaxies floated. The universe itself was expanding. The very fabric of space-time was stretching, carrying the galaxies along with it for the ride. To visualize this, do not think of galaxies flying apart through empty space like shrapnel from an explosion. That is the wrong picture. Imagine instead a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. A raisin close to you moves away slowly. A raisin on the far side of the loaf moves away much faster. Crucially, from the perspective of time's anytime single raisin, it appears as if all the others are rushing away from it. There is no center to this expansion. The expansion is happening everywhere, in the very fabric of the dough itself. In this analogy, we are on one raisin, and the distant galaxies are the others. The space between us is the dough, and it is continuously expanding. This discovery had a mind-bending implication. If the universe is expanding today, then yesterday it must have been smaller, and the day before that, smaller still. If you run the cosmic movie in reverse, all of the galaxies, all of space and time, all matter and energy must rush back together into a single, infinitesimally small, infinitely hot, and infinitely dense point. This was the inescapable logic that led to the theory of the Big Bang. The universe had a beginning. It has an age. And this finite age is the key to finally answering our question. It is the reason we must speak not of the universe, but of the observable universe. Because the cosmos has a finite age currently calculated to be 13.8 billion years, there is a fundamental limit to what we can see. Imagine standing in the middle of a vast, dark forest. At the moment of the Big Bang, a brilliant flash of light illuminated the entire forest. That light has been traveling outwards in all directions ever since. The light from trees 1 foot away reaches you almost instantly. The light from trees a mile away takes a few seconds. The light from a tree 8 billion light years away, if it had been stationary, would only be reaching you right now. Anything beyond that distance, any light that would have had to travel for longer than 13.8 billion years to reach you, simply hasn't arrived yet. It is still in transit. This creates a sphere of visibility around us, a cosmic horizon. The edge of this sphere is the most distant point from which light has had time to reach us over the entire age of the cosmos. This sphere is the observable universe. So, is the answer to our question simply 13.8 billion light years? Is the radius of our observable sphere 13.8 billion light years, making its diameter 27.6 billion light years? The answer, astonishingly, is no. The reality is far, far larger. And the reason for this brings us back to Hubble's expanding dough. The light from the most distant galaxies we can see did not travel through a static, unchanging space. It journeyed through a universe that was actively stretching, expanding every single moment of its long voyage. This is a critical, and often misunderstood, point. Let's create a more precise analogy. Imagine two explorers, you and a friend, standing on an enormous, infinitely stretchable rubber sheet. Your friend is some distance away. You both have magical boots that nail you to your specific spot on the rubber. Your friend sends a tiny, robotic ant walking towards you. The ant walks at a constant speed of 1 inch per second, times relative to the rubber surface beneath it, asterisk. But as the ant begins its journey, a powerful machine starts stretching the entire rubber sheet, doubling its size every second. The ant bravely walks on, covering its 1 inch of rubber every second. But the very rubber it is walking on is being stretched out behind it and in front of it. The destination you is constantly moving farther and farther away. The ant's journey will be much longer than it would have been on a static sheet. And by the time the ant finally reaches you, its starting point, where your friend still stands, will be a colossal distance away, much farther than the total distance the ant itself has walked. In this analogy, the ant is a photon of light, traveling at the cosmic speed limit. We are one explorer, and the galaxy that emitted the photon is the other. The stretching rubber sheet is the expanding fabric of space-time. The light from the most distant object we can possibly see was emitted about 380,000 years after the Big Bang. This light is not from a star or a galaxy. It comes from a time when the entire universe was a hot, dense, opaque fog of plasma. As the universe expanded and cooled, it reached a point where protons and electrons could finally combine to form the first neutral atoms. At this moment, the cosmos suddenly became transparent. The light that had been trapped within the plasma was set free, and it has been traveling across the cosmos ever since. Today, we detect this ancient light as a faint, uniform glow in all directions. It is called the cosmic microwave background, or the CMB. It is the oldest light in existence, the baby picture of our universe. This is the ultimate edge of our vision, the inner surface of our observable sphere. When the light from the CMB that is just now reaching our telescopes began its journey, the patch of space that emitted it was about 42 million light-years away from the patch of space that would one day become our Milky Way galaxy. For 13.8 billion years, those photons have traveled across the expanding cosmos to reach us. During that immense span of time, the very space between us and the source of that light has continued to stretch and expand. Cosmologists, using our most sophisticated models of the universe, factoring in the influence of dark matter and the accelerating expansion driven by dark energy, can calculate how much that intervening space has stretched. The result is breathtaking. That patch of space, which was a mere 42 million light-years away when it released the light we see today, is now 46.5 billion light-years away from us. It has been carried away by the expansion of space itself, just like the distant raisin in the rising bread. This gives us the true radius of the observable universe. It is not 13.8 billion light-years, it is 46.5 billion light-years. The total diameter of the sphere of reality we can, in principle, ever see is therefore a mind-numbing 93 billion light-years. Let this number sink in. 93 billion light-years. A light-year is the distance light travels in a year, nearly 6 trillion miles. Our entire Milky Way galaxy, with its hundreds of billions of stars, is about 100,000 light-years across. If you were to represent the Milky Way as the size of a single grain of sand, the observable universe would be a sphere more than 5 miles across. And within this sphere, there are an estimated 2 trillion other galaxies, each one a grain of sand, each containing hundreds of billions of suns, and likely trillions of planets. This is the scale of our cosmic fishbowl. It is the boundary of our knowledge, the limit of our sight. But this leads to the most profound question of all. What lies beyond the horizon? What is outside the observable universe? And here, we leave the realm of observation and enter the world of informed, yet breathtaking, speculation. The simplest and most widely accepted answer relies on a concept called the cosmological principle. This is the assumption that, on the largest scales, the universe is roughly the same everywhere. It is homogeneous and isotropic, meaning it has no special location and looks the same in every direction. Our cosmic neighborhood shouldn't be special. Therefore, the universe beyond our horizon is likely just more universe, more galaxies, more clusters, more cosmic web, stretching on, perhaps forever. Our 9.3 billion light-year sphere of observation is not a physical edge. It is simply our personal horizon. An alien in a galaxy 60 billion light-years away from us would have its own observable universe, its own sphere of visibility. Its sphere would include parts of the cosmos we can see, but also vast regions that are forever beyond our horizon. Likewise, we can see regions of the cosmos that are forever beyond its sight. It is like being on a ship in the middle of a vast ocean. You can see to the horizon in every direction, but you know that the ocean does not end there. A ship just beyond your horizon has its own horizon and sees a patch of ocean you cannot. The true ocean of reality is far, far larger than any single observer's view. But how much larger? This is where the theory of cosmic inflation enters the picture, and the numbers become truly beyond all human comprehension. Inflation was proposed in the 1980s by physicists like Alan Guth to solve some deep puzzles about our universe, such as why it is so remarkably flat and uniform. The theory posits that in the very first fraction of a second after the Big Bang, in a sliver of time, so small it makes a nanosecond look like an eternity, the universe underwent a period of hyper-accelerated, exponential expansion. During this inflationary epoch, a region of space smaller than a proton may have been stretched to a size larger than our entire observable universe today. It was as if the fabric of space-time itself was expanded faster than the speed of light. This does not violate Einstein's theory of relativity, which states that nothing can travel times through time-space faster than light. Inflation was the expansion times of time-space itself, which has no such speed limit. If inflation theory is correct, then the totality of the universe, the entire overarching reality, is incomprehensibly larger than the 9.3 billion light-year patch we can see. Calculations based on inflation suggest the full universe is at least 10 to the power of 23 times larger than our observable universe. This is a 1 followed by 23 zeros. It is a number so large that if our observable universe were the size of a single subatomic particle, the true universe would be larger than the observable universe is today. It is a scale so gargantuan that, for all practical purposes, the universe might as well be infinite. Our entire cosmic horizon, with its 2 trillion galaxies, would be like a single atom in the Pacific Ocean, a speck of dust in a reality without end. And the theories do not stop there. Some models of inflation, known as eternal inflation, suggest that the inflationary process may not have stopped everywhere at once. Perhaps it is still happening in other, impossibly distant regions of the cosmos. New universes, or pocket universes, could be budding off from this inflating background, each one a bubble of space-time that cools and allows galaxies to form. Our entire universe could be just one bubble in a vast, frothing sea of other universes, a multiverse of cosmic bubbles, each potentially with its own unique laws of physics, its own unique set of dimensions. This is the frontier of modern cosmology, a place where physics and philosophy merge, where the answers to our questions about size and scale lead us to contemplate the very nature of existence itself. We begin by asking how big our universe is, and we end by asking if our universe is the only one. So how can we possibly wrap our minds around this scale? Scientists often use a logarithmic map to visualize it. In the center, we place our tiny home, the Earth. Moving outwards, we cross the orbit of the Moon, then the planets of our solar system. Beyond Neptune lies the Kuiper Belt, and farther still, the vast, spherical Oort cloud, the reservoir of comets, marking the outer gravitational boundary of our Sunday. This solar system, which takes light years to cross, is just our immediate home. Far beyond it, we encounter our closest stellar neighbors in the Milky Way galaxy. Zooming out further, our entire galaxy, with its beautiful spiral arms, becomes a single object. It is just one of the larger members of the local group, a collection of a few dozen galaxies, including Andromeda, bound together by gravity. Pulling back again, our local group is revealed to be a mere suburb on the outskirts of the immense Virgo supercluster, a sprawling collection of thousands of galaxies. Even this colossal structure is just one tendril in an even grander architecture. Superclusters are woven together into unimaginably long filaments and walls of galaxies, separated by colossal voids of near-perfect emptiness. This is the cosmic web, the largest known structure in the universe, and as we pull back to the final, ultimate view, even this magnificent web dissolves into a uniform, mottled glow. We have reached the edge of our vision. We have arrived at the cosmic microwave background, the afterglow of creation, the inner surface of our 9.3 billion light-year sphere. This is the size of the observable universe. It is the portrait of everything we can ever hope to see. We began our journey with a single point of light in the night sky. We end it here, at the boundary of space-time, with a number 93 billion light-years that is both a triumphant achievement of human intellect and a humbling reminder of our cosmic insignificance. For millennia, we have strained to find our place in the cosmos. We have shifted from the center of everything to a small planet orbiting a nondescript star in a remote spiral arm of a common galaxy, in a small galactic group, lost in a supercluster within a universe so vast it may well be infinite. And yet, this same knowledge that makes us feel so small is also what makes our existence so profound. On this tiny speck of rock and water, in this forgotten corner of the cosmos, a part of the universe has woken up. Matter has become self-aware. Stardust has evolved into beings who can look back out at the vastness, wield the power of mathematics and the laws of physics, and ask the most audacious question of all: how big are you? The answer, we have found, is bigger than we ever dreamed, far bigger than we can truly comprehend. And the ultimate truth may be that the universe we can see is but an infinitesimal fraction of a reality so grand, so complex, and so utterly strange that our quest to understand it has only just begun. The night sky is not a ceiling. It is an invitation to an ocean of possibilities, stretching on, perhaps, for all of eternity.